Good afternoon and welcome to the 10th session of the first edition of Technical MasterTalks. Today's session will be dedicated to the Department of Civil Engineering, Architecture and Environment. I'm Rafaela, a master's student at Technico, and I'll be the moderator of this talk. We'll have some time for your questions at the end of the talk, and then we encourage you to know more about each of the department's masters, as well as international opportunities, career development, and student support at Salão Nobre on our Master's Day. First, I would like you to thank Professor João Ramôa Correia for accepting our invite to be here with us today. Professor João is a full professor at the department and currently the coordinator of the Composite Research Group. His main field of research is the mechanical behavior of fibrous composite material systems, connecting technology, long-term performance, durability, fire behavior, and sustainability. He was also honored with 3 international prizes related to his field of research and published about 200 scientific articles. We will have the pleasure to hear what Professor João has to say about the application of these materials in civil engineering and how we as students can be part of it. Thank you.
Thank you very much, Rafaela. Thank you everyone for attending this lecture or talk. So I was asked to present, in fact, a 2-part talk, and so I tried to address this request. So I will first present you very briefly our department, DEC Civil, and the Master in Civil Engineering, which is the main master in our department. In the second part, I will show some highlights of our research activity on composites for civil engineering applications. So let me then summarize some highlights of our department. So DEC Civil is one of the founding departments of IST, and it's one of the largest. We have around 120 faculty members, and their background is, I would say, rather diverse. So we come from different areas of civil engineering, but we also have colleagues from environmental engineering, from geography, architecture, and I think this is a very good asset for our students, this diversity in terms of background of faculty members. We host at bachelor and master levels around 2,000 students in an environment that I would say is rather international. Yesterday, my colleague Carlos Tiago just mentioned we hosted 400 Erasmus students in civil engineering and architecture. And of course, this level of internationalization increases at the PhD level. This is the overview of the teaching programs that we offer at the different levels. For the master, and I will focus later on civil engineering, we also have offers in environmental engineering, together with chemical and mechanical engineering departments, territorial management and urban studies, transportation systems, and the integrated master in architecture. Well, I'm sure that most of you are aware of the resources that IST offers and also our department to our students, not only for teaching activities, but for other areas that are important in their lives, sports, students' associations, and I think this completes their experience at IST. For research infrastructure, I think we are quite well equipped in terms of laboratories. Here I listed, and you see some images of laboratories in different areas of civil engineering. This is very important for teaching activities, experimental classes, but also for research. So I would say that most students, or many students at least, develop their master dissertations in these labs. Well, here you can see the overview of the Master in Civil Engineering. Now I will focus specifically in this offer. It's structured according to the Masters of IST, the rules that were defined by the school. So we have a 2-year 4-semester master, a common course structure with around 70 ECTS in blue, elective courses that are related with the area of expertise. I will come to this next. 21 ECTS in green, and finally a dissertation of 30 ECTS in the last semester. Here you can see the study plan, detailed study plan. So I will let you read the names of the courses, while I will highlight that the first semester is common to all areas of expertise. Okay, so you see the courses from the different areas of civil engineering that I will mention next. Second semester and third, students already have to select their area of expertise. So we have these green boxes, okay? And also they still have some common courses from this core that we think it's important for the background of any civil engineer. In orange, you can see some free options that students can select, either from civil engineering or from other departments, including a minor. And then finally, the dissertation that covers the last semester. So as I was saying, students in our master can select, or they have to select, one of these 5 areas of expertise: construction, structures, hydraulics and water resources, geotechnics, and urban planning and transports. And I think this reflects well the background and the breadth and scope of what we understand as what a civil engineer should be. Okay, so, and I think also this is reflected in the elective courses that students have, namely in these free options. And this is different from the masters in civil engineering that are offered in other universities in the country, that are more narrow than what we offer. Well, in terms of career opportunities, I listed on your left-hand side the areas of intervention typical of a civil engineer, and on your right-hand side, the stakeholders or agents where these activities can be developed. So you can see that civil engineers can operate in very different areas. So construction, rehabilitation, geotechnical works, water supply and sanitation systems, materials and components, recycling and management of waste, urban planning, transports, logistics, management and maintenance of projects, works and assets, and also research. Okay? And they can do it in these different roles: public and local administration, project management companies, design offices, contractors, supervision companies, consultancy, real estate, labs, and also building their own company. We have several examples of success of students from our master who started quite successful business in civil engineering and related areas. Well, in terms of career opportunities, well, you are aware of the recent past, okay? My personal view is that the future prospects should be optimistic, okay? So we know that there is a big shortage of civil engineers worldwide, not only in Portugal, but also in Europe, in the US. So we are shortage of civil engineers. Wages are starting to increase, fortunately, okay? And there are many big projects, public, private, long-term investments scheduled for the next 2 decades. So I think there are lots of things to do for civil engineers. Another aspect that I think is worth highlighting is that we civil engineers are essential to address many of the future challenges of mankind. And if you think about some of these challenges, civil engineers, they are needed there. So we are needed for smart cities. We are needed to develop these complex and large-scale infrastructure systems. The industry is in a transition towards digitalization, robotization. At the same time, we need to preserve both our built and natural heritage. And civil engineers, they will also be extremely important to respond to societal changes, but also to address a number of problems, natural risks, and climate change that is there. okay? And this will impact not only our daily life, but we need to prepare our infrastructure and buildings for all these changes. So here I illustrated some of the problems that we will have to help solving. Drafts, floods, water supply, coastal protection. We have a big coast. We know that this will happen, okay? And civil engineers will be needed to address these problems. Let me finish this first part to show you how we have performed in recent years in international university rankings. So we are very proud of what we achieved. So we have consistently ranked in Europe, in Shanghai and Taiwan rankings in the top 10. And with, I would say, limited resources compared to our competitors in Europe and worldwide, I think this is something that we should be proud of, okay? And I think our students benefit from this performance, and they also contribute to this performance, okay? Okay, so let me move now to the second part, okay? So in 20 minutes, and I will try to fill the time that was allocated, it's not easy to explain research on composites because most of you perhaps are not aware of what composites are. So I will try first to explain what these materials are, how they were introduced in different industries during the years, how they can be applied in civil engineering, what are the main challenges for such application, and how we at Técnico have been addressing the unknowns and those challenges in innovative products. So starting with a brief historical overview. So first of all, what are composites? Okay, and the word composite means combining, okay? Bringing together different materials, making use of their main advantages, okay? And this idea of composites is very old, okay? The first known composite material in history are these adobes, used or developed in Mesopotamia almost 7,000 years ago. The idea was brilliant. So these adobes were used for construction of houses, sanitary, different applications, and they were basically mud that was put to dry under the sun. And during the drying process, these bricks, they cracked due to shrinkage. And the main idea was, let's try to introduce fiber reinforcement that resists tensile stresses and that prevents these cracks. Okay, so this is basically the same that we are doing now with modern composites. We use fiber reinforcement, not natural but synthetic, to reinforce another material that is not mud but a resin. Okay? So modern composites, well, it took a while. So we had first to wait for the plastics industry to develop in the 1930s and 40s. And then we could use these modern composites in first naval and aerospace industries that still are large consumers of these materials. For instance, due to their lightness, which is very useful for these specific industries. In the 50s, they were introduced in automotive and oil industries, where they still are used very often. And in construction, quite interestingly, there was a first attempt in the 60s to use composite materials. Here I brought three of some of these first stage applications. You can see with the rather futuristic architecture. Okay? Architects were in fact extremely curious and they were motivated by the potential of these materials, by the shapes they could cope. But this initial effort ended up being abandoned for two reasons. First, the cost. The material was very expensive by then. And second, people or engineers were not aware of how to design these materials. There was not enough technical knowledge. Well, in the 70s, there was an extension of these products to new markets. So racket tennis, okay, so the graphite tennis rackets are from this period. skis, and also surfboards. Okay? If you look at this surfboard, it's basically a sandwich panel as this one. Okay? So two face sheets of composite, and in the middle, a polymeric foam. It's the same. Okay, so we get to the 80s and 90s when these materials, again, there was a resurged interest by civil engineering. And here I list the three main reasons. The first one, there was a huge need to rehabilitate civil infrastructure. So most structures or a large stock of buildings and bridges had been built after World War II, and their corrosion problems, namely, started to appear with big relevance in this period. So it was clear that new materials, more durable, less prone to corrosion, were needed. Second reason, the interest for having faster construction. And this occurred together with a reduction in manufacturing costs due to technological developments in processing. So these three features that composites offer, high strength, lightness, and durability, together with more affordable costs, explain this new interest from the construction industry that lasted since these 80s and 90s. So let me now show what are the key products, okay, that are available for civil engineering. And I organized them here in 4 groups, okay, and I will show you then examples. So the first application is the internal reinforcement of concrete structures. So bars, okay, instead of using steel bars, we can use FRP bars. So FRP stands for fiber reinforced polymer, okay. Second example is the external strengthening of existing structures. This is now a well-established technique. Most design offices and many contractors use it regularly. Okay? Strips, such as this one, made of carbon fiber, okay, with epoxy, or sheets like this one, okay, that is dry, okay, and then needs to be bonded to the substrate, are being used not only with concrete structures, but also with other structural materials. And here, 2 different solutions where we rely more on composites. What we call hybrid structures, where components made of composite, for instance, this structure here has one of these decks made of composite, okay? But it is connected to steel girders. So they work together. So this is why we name these structures hybrid. And then we have all composite structures. Okay, so structures where all components are composite. Okay, and for these 2 cases, we have panels like these ones and profiles. Okay. So let me now introduce some features for each of these products. Okay, I will not give technical details. Okay, just a glimpse of what's available. So for rebars, and I try to be not too technical, so they are basically made of glass fiber roofings. This means actual fibers only, with a matrix of vinyl ester. Okay, you have different resins. Vinyl ester is, let's say, an improved resin compared to polyester, which is the custom or standard grade, because concrete is a relatively aggressive environment, so we need a slightly improved resin. Well, they are supplied in diameter similar to steel bars. The surface finishing initially was a problem. The adherence to concrete was not good, but now, as you can see, either with ribs or with sand coating, the adherence to concrete is enough. Okay? And these are the geometries that you have available, so straight bars and also bars with bends to produce stirrups or ties. Here are some examples of applications. Bridge decks. This is useful in cold regions where de-icing salts that are highly corrosive can be used in the winter. And here, maritime structures. Okay, this one in Portugal, actually, okay, which due to the salt water, it's a big advantage of using these rebars. Now, the properties that I did not mention. So see, tensile strength, 1,200 MPa. This depends on the amount of fibers and the type of fibers, but this is a typical value. So it's about 3 times what we have for steel, with a self-weight that is 4 to 5 times less. Okay? There is always a disadvantage, otherwise we would always use this type of bars instead of steel, and one is the elastic modulus. Okay? They are more deformable, okay? If they are made of glass fibers. Okay, the second product are strengthening strips and sheets. So strips like this one are made of carbon fibers. They resist more than glass, and they are extremely lightweight, as you see. Okay? The tensile strength in this case is 2,500 MPa in this range, so 10 times more than steel, okay? With an elastic modulus that is similar to steel. Okay? So this is why it's now a standard solution for strengthening. Okay? So these strips and also bars, they are very easily applied by bonding adhesive and then sticking the element to the substrate that we need to, or that we want to increase the capacity. The other product are these sheets. As I mentioned, dry sheets, okay, with fibers that can be applied in different directions depending on your needs. And they are simply molded and cured on site with epoxy matrix. So the advantage is that if I want to reinforce or strengthen this member, I can apply it like this. Okay? So I can mold it to complex shapes. So here you can see some applications, okay, in flexural strengthening of beams and slabs. And here another application of sheets for the confinement of columns. This is very important for to improve the seismic resistance, to confine vertical members, and very effective. Okay, the third product that I mentioned are profiles. Okay, here what we call the first generation profiles, so thin-walled sections. They look pretty much similar to steel profiles, but they are much lighter, okay, 4 times lighter, similar strength, but lower stiffness. Okay, so this changes the way they are designed. On your right-hand side, you can see what we call the second generation panels or profiles with 2D section, so used for decks, for instance, of bridges. This image shows, and also this profile that I brought, shows the internal constitution of these profiles. So you can see rovings, so longitudinal fibers, combined with mats with fibers in different directions. And the principle in composites is that we can cook these ingredients, so use fibers in the directions that we need, okay, to obtain the strength and stiffness that copes with the design requirements. Here you can see some applications of these profiles in new construction and also in rehabilitation. Replacement of degraded bridge decks, where we can keep the girders, or in the rehabilitation of timber floors and roofs. Okay, the final of these products are sandwich panels. Okay, so I already explained more or less the concept. So you have, in the simplest form, 2 face sheets of composite, which more or less behave like the flanges of an I section. And in the middle, we have a very lightweight material that provides the lever arm for the face sheets. So it's the type of solution compared to profiles that gives us the highest properties at the lowest weight. Okay? Here we can use balsa wood, extremely lightweight, and different polymeric foams. So let me show you some examples of structures that have been built. This very nice roof that was installed over this glass facade. So it had to be very light and with a double curvature, so complex shape. this road bridge with exactly this type of solution, okay, so balsa wood, which had to be built very quickly to minimize traffic disruption. So a very light solution was selected due to this reason, and also because the abutments could not resist the loads of a conventional solution. And also this roof in Saudi Arabia, where besides lightness and complex shape, it was also selected because it provided translucency. So in terms of architecture, it was a very nice, very nice solution. Okay, so now that you know what are composites, let me very briefly detail the main challenges, in my view, that these materials face. Okay, these are quite complex issues. Okay, I would need more time, but I would like you to know what's at stake. Okay, so I showed composites and I showed buildings. Okay, and in buildings we need fire safety. So fire behavior is a major concern here. Okay, so these materials, they are flammable, so they burn, they release heat, smoke, and also the material properties, they decrease at elevated temperature. Okay, so this is one of the key points for any of these products. If they are used in buildings, this needs to be addressed. So we need protection systems, the same way we need for steel structures, but we need to know how to design them. And while for steel there are already rules that have been validated, checked, this is where we still have a long way to go. A second challenge, durability. So this seems a bit paradoxical, right? So I was saying that durability is a key advantage, and now it's a challenge, and it's in fact a challenge, okay? Because these materials, they have proven good performance in quite harsh environments. But in all those industries that I mentioned, we don't need to design for 50 years or even 100 years. And this is a big difference to civil engineering. Okay? And I should also say that after looking at the codes that are used to design structures in those industries, I think our codes are better. Okay? Reliability of our structures is guaranteed in a different way, in a more comprehensive way. So we know that some degradation occurs, but we still don't know how much it will be after 50 or 100 years. So we still don't have reliable design models also for durability design. Third big challenge is sustainability. Okay, so now all solutions that we adopt in all engineering problems, we need to know what will be the impact and compare to alternatives. And composites, for different reasons, they cause environmental impacts. One that is very important has to do with the type of resins that we use, which are thermosets. And it's difficult, not to say impossible, to reprocess in practice this type of resins. So alternatives are being pursued that need to be assessed, of course, throughout the life cycle. But the trend and the industry trend right now is really towards greener and circular composites. This means bio-based composites, composites with thermoplastic resins, so different routes are being pursued here. Okay, so in these very last minutes, let me show some of the work that we have been doing in these areas. So first of all, what has been the research team. So this group was started in 2008, so it's 15 years old already. Until now, we were 3 professors. Now, João Firmo moved to concrete, but still working in composites. We have 4 postdoc researchers that have been working in this area for already quite some years. We have 8 PhD students, some already ending, some starting, and every year we host, I don't have a good number, but around 6 master students every year. Here I listed the research topics organized by those 4 products. I don't expect you to read, but these are the topics that have been relevant at an international level. And I marked in blue the topics in which we worked, or at least we gave some contributions. One interesting thing is that those challenges that I mentioned, they are in all those products. So durability, fire behavior, sustainability, it's everywhere, okay? So I will just, because the time is short, I will just show some highlights of what we did, especially here in profiles, but not only. So of course, this was the starting point. We had to understand the mechanics of these materials. So the material behavior, the structural behavior of different members, columns, beams. Some of the phenomena are similar to what we have in other structural materials. Local buckling, Euler buckling, lateral torsional buckling, so web crippling. But of course, materials are different, the phenomena are triggered in a different way. We also worked on connections, bonded, and here you can see bolted. This is also a bottleneck, let's say, of these materials because they are orthotropic, so they don't behave the same in all directions. And here the route that we pursued was basically to adopt hybrid connections. So let's include stainless steel components that are able to dissipate energy, to have nonlinear deformations, combine them with composite materials. This proved to be quite interesting, and we upscaled this to the structural level. These are very recent tests that we did in ISPRA, in the Joint Research Center for an Italian company, where we designed for them optimized connections with this concept. And here, this frame was tested in a reaction frame, so under horizontal loads, to assess its ability to resist wind loads, but also seismic loads. In another project we assessed the same problem with also this type of connections, and we did tests in our shaking table. So here the idea was to see if it resisted our 1755 earthquake, actually the double in terms of accelerations. So we were about 15 meters away, okay? And it resisted. Okay, moving down in terms of scale, durability. Okay, this for me is one of the key points that we need to improve in terms of knowledge. So what we have been doing in recent years and already quite some time ago, so we need to check or to understand what happens due to different environmental agents. We are doing this for natural weathering. So this is a project that we are developing with different stations located in different areas in Portugal, where the aggressiveness of different environments is different. But we cannot wait 20 years or 50 years. So we are also doing artificial weathering in chambers. And here the idea is to cross-correlate the degradation in terms of performance between the two types of weathering. And at the same time, we are looking into the oldest structures that have been built in Portugal, that are 20 years, and we are collecting material to understand the degradation under real-scale aging. For fire, we also did quite a lot of research, so to understand mechanical behavior at elevated temperature, and also at the member level, what happens when members are exposed to loads and fire at the same time. So both experiments, and here with colleagues from computational mechanics, the simulation, which is quite complex, of this problem. And for sustainability, this was a project led by Mário Garrido, the bio-based resin systems. And here what's interesting to tell is that we, of course, did not have the expertise. So we asked collaboration of colleagues from chemical engineering department. So big challenges involve teams with people from different areas. So they helped us, and we had a brilliant student. He was civil engineer, structural civil engineer, and he had the courage to go to a chemical lab to synthesize bio-based resins. So he was able to do it, and the idea here is to use renewable resources instead of oil to produce our resins. And it was quite successful, as I will show in one of the last slides. Well, to finalize, I'm about to finish. We have always tried to translate this knowledge to applied research projects, to ask or to respond to challenges and requests by companies. One of these projects was the ClickHouse project. So this was developed with Minho and also with Alto, a company in Maya. So the idea here was to develop an emergency house, all composite, that could be built in one day by 3 workers without any relevant equipment. Okay? So we had collaboration of colleagues from architecture for the design of the layout, and then all the facilities like water supply, acoustics, thermal comfort, all these aspects were addressed experimentally and then based on simulation. So this is the final prototype that was developed. Another project was this hybrid footbridge that was built in Viseu, where our student by then came from. It combines steel girders that you can see here. They were produced in a shop, lifted with lightweight equipment, positioned over the abutments, and then you can see these panels that were brought by 2 men very easily and simply bonded on site. So this was built in a few hours. So this is the bridge after being completed, and here you can see how it is integrated in the landscape. Another project, another hybrid bridge, here different concept. Composites here are used as girders, and they were bonded to a very thin deck with only 4 centimeters of thickness of steel fiber reinforced concrete, so no rebars whatsoever. So we did tests in a small scale prototype, and then you can see here the full scale prototype being tested for comfort, so for comfort of pedestrians. Here is the construction. The final load tests with twice the characteristic load that is necessary for pedestrian bridges. And here, the bridge, it's there. It will be 10 years old this year. Okay, it's in Ovar. Another interesting project, we called it the Easy Floor. So the concept was to develop sandwich panels for rehabilitation of building floors and use composite to cope with different requirements. So not only structural, but also acoustics, building physics with additional layers if necessary. The main feature of these panels, we had also a brilliant student who worked on this project, was to develop these snap fit connections. So this was printed in 3D printer machine, and the idea is that these panels are installed like this. Okay? They can be easily dismounted if necessary. More practical project to address a real problem. Many of these highway underpasses, agricultural and hydraulic underpasses, in the 80s and 90s were built with this Armco system. So it's a corrugated steel sheet, which has, as expected, huge corrosion problems right now. So this was taken from, I think it's A17 highway. There was a collapse several years ago, and it was disrupted for about 1 month. It's one of the main highway axes in the north of Portugal. So it was not our idea, but we helped this company in this project to apply FRP culverts, composite culverts, as you see here, that are installed inside the structure that has these problems, and then the space in between, which is almost fit, is then injected with grout. So here you can see the tests that were carried out in our lab, the numerical models that were developed, and here the completed structure. And the last project, so as I mentioned, this bottle of bio-based resin was then applied at an industrial scale in with this company, S&P Clever, in Elvas, to produce strengthening strips like these ones. Okay? So instead of epoxy, our bio-based resin. Okay? And then it was proved by tests that it behaved in the short term as the conventional strips. So just a final word to show the recognition that our students had in many of these projects. So 4 of them received the Cecil University's Prize for Master students. Also, students that received this important award for PhD thesis, Inês, Rosa, Luísa Castilho, Best Student Paper Award, Beatriz Tavares da Silva and Inês Rosa and David Martins for the Portuguese Association of Mechanics. And for innovation, they were also recognized. José Gonilha, David Martins, and they received this important award from the Board of Engineers, and I could mention another awards as well. So thank you for your attention. And for those who want to know more about composites, you may also attend this conference next year in Lisbon.
Thank you, Professor, for this informative talk. I'd like to start to ask the audience if you have any questions. No? Feel free to ask anything.
Otherwise, I will talk for more 15 minutes on composites.
Yes, well, since this is a talk designed for prospective master students, I would like to know if you have any advice on, first part of my question would be advice on how to choose a good supervisor for your master thesis, advice for students on how to choose.
This is a tricky question. So I would say first of all, talk to see the topics, okay? And this is the main point, select a topic that motivates you to work for 6 months, okay? It's not a PhD, it's not 4 years or 3 years, but 6 months is a lot of time, okay? So select a topic that really motivates you, and a topic in which also the methods that are going to be used suit your interests. Okay, someone who does not want to put their hands in the lab or to produce materials, it's better to do a numerical work or a different type of approach. So first the topic, of course, the supervisor, it's important that supports the student, and it's important that knows about the topic, okay? So I think it's important that students be aware of who the supervisors are, and but I don't think this is a problem in our department. I think we have excellent supervisors in all areas.
And on the other hand, what do you value if someone wants to do a master with you? What does one have to do a master with you? What do you value as a student?
Well, I value the interest in the topic. Okay, if the student is really curious about the topic. Okay, so I don't ask about grades. I don't ask what is your grade. If you want to do this work with me, if you are curious, let's do it. That's it.
So motivation is key.
Yes.
What about double degrees in this master? Is it a possibility?
Yes, it's a possibility. Well, I should know this by heart because in the last term of the executive committee of my department, I was in charge of this. We have some double degrees. The last one that was established was with Naples, if I'm right, already in this new executive committee. So there are possibilities there, but I'm not really convinced that students are pursuing very much this option. Okay, I don't have the numbers, but in fact, in terms of mobility, what's happening right now is that we are receiving a lot of students. As I mentioned, 400, civil and architecture. The outgoing students are not that much. I think there are different reasons. Economic reasons are definitely one. Okay, so I would say for those who can, I definitely recommend. I did Erasmus for 6 months. It was an excellent experience. I could realize how good our degree is here at IST. So how complete is our background education. So I strongly recommend. Double degrees are also an alternative that students can check, yes.
Okay, so this is it. This is the end of our 10 MasterTalk session. We will have the next one in July for the departments of physics with the professor Vitor Cardoso. So if you are interested, you can already sign up. Thank you everyone once again. I would like you to encourage you once more to join our Master Days at Salão Nobre. to meet with other professors and students. Thank you so much for attending.